Okay. Well, hello to those watching online. It's semester 1, 2023, and this is a revision seminar for differential equations. Well, let's get started. I've already had a chat to all these people who are here and online about what they want to talk about. And we're going to start with bifurcation-y stuff. So I'm going to share my camera and we'll get started. All right. Okay, so as I said to all these people, but for those watching on the video, this is new to me in the last few years. I'm still figuring it out. So if you have any more questions about it, then come and talk and we'll nut it out, or talk to your lecturer and then bring the answer back to me and let me know so I can pass it on to other people. But I'm pretty okay with the vibe of it. Back in Maths 1B, we actually did differential equations that are similar to the ones that are turning up in this area. So in Maths 1B, you did things like something like that. And this is called an autonomous differential equation because the variable t is the thing that's causing x to change because I'm differentiating with respect to it. But the answer for the derivative does not depend on knowing what t is. It only depends on the output variable. So we've got t is my input, x is my output, and dx on dt only depends on the output. There you go. So that's called an autonomous differential equation. Autonomous meaning acting on its own in English. And so the x is acting on its own without influence from the t. It is acting with influence from the t, but that's not what it looks like in this equation here. Okay. So back in Maths 1B, what we did, I'm going to change it slightly. What we did is we thought, well, this is the derivative with respect to t, so the critical points on the graph will happen when the derivative is 0, and that's still going to happen when the derivative is 0, but this time I can only make the derivative 0 by changing what x is rather than by changing what t is compared to what we used to do. And so therefore you get x minus 1 squared equals 0, and you get x equals 0 and x equals 1. So at any moment where the x coordinate is 0, regardless of what the t is at that time, regardless of what the t is, that will be a critical point on the graph. So all the critical points will have these x coordinates. And when I say x, that's really the y, that's the output. The output will be 0 or 1 whenever the derivative is 0. Okay, and what we normally do is we draw a single line of all the options for what x could be. I'm going to draw it vertically. In Maths 1B, they draw it horizontally, but this matches better with what goes on in this course. And here's 0, and here's 1. And I imagine as t moves, where does the x move along this line? And it's one of the pictures of functions that we have. Instead of drawing them as graphs, we can think of them as dynamic, where t changing, there's another axis over here for t, and as the t moves, so does the x. It does whatever it does. T moves forward and x does whatever it needs to do. And so you can imagine that instead of thinking of it as a t-axis and an x-axis, you can think of it as time moving forwards and watching where the little dot goes. So here's the thing. If dx on dt is positive, that must mean that as t moves forward, x goes up. And if dx on dt is negative, that means that as t moves forward, x goes down. So all, in inverted commas, I need to do is figure out whether dx on dt is positive or negative, and then I'll be able to decide whether it's going up or down at any given moment. And most people would actually draw this graph and just look at where it's positive and negative. And so they'd go. They actually would draw this picture. This is x and this is dx on dt. And it's x squared minus 1, which looks like that, because the squared here makes it touch the x-axis like a parabola at that point there. And the fact that there's no squared there means it goes through. Okay, and so it's positive here and negative and positive here. Sorry, it's negative here. Damn you, David. It's negative here and positive here and positive here. Like it's below the axis here, which means it's negative. It's above the axis here, which means it's positive. Above the axis here, which means it's positive. So when I look at this, it's going this way and this way and this way. Yay. How are we feeling? Sweet. I'm just going to put them in color because that appeals to me. Oh. Just color coding. From one page to the other, so if whoever reads this later can notice that, hopefully. Yay. Okay. Cool, and that's great, and this is where we stopped in Maths 1B. Other than saying, if at time equals 0, x was a half, where would x go? It would go towards 1. And that's what we would normally do. But in this course, in this course, there's like an unknown parameter in this formula, and the different values of that parameter would cause this differential equation to have different critical points. And so you're going to draw a diagram that says for each value of the parameter, what are the critical points? Just kind of, I wish I had an example. I could do one of the ones in one of the assignments or something, maybe. For example, this one, which was in Tute 4, I think. This is different depending on what beta is. Like if beta is 0, then we're great. We know how to deal with that. Yeah. Actually, no, just a second. I've forgotten something. We're going to look closer at this because you don't have to draw the sign diagram to make a decision about whether it's going from minus, whether you're going to have a minus or a plus here. Because at this point here, it's going from, we know that it's 0 at this spot, that the x under t is 0 here. And therefore it's sort of either crossing the x-axis in one direction, or it's touching it, or it's crossing in the other direction. And in order for it to cross the x-axis in this direction, the derivative of this with respect to x has to be positive, because that's going upwards there. And so what that means is, now here we are in Ds2, we've added an extra bit of information. We call this f of x. And if we find out what f dashed of x is, keep the x, differentiate this. And then differentiate the x and keep this. Now, when x is 0, I get 1 times negative 1, which is not what it was supposed to be. What have I done wrong, people? Aha, thank you. Good listening and watching. All right, yeah, Just a second. So we kept the x and differentiated that one, and then we differentiated the x and kept that, and it had a squared, so we had to keep the squared. Gotcha. Like that. Cool. So this time we get, when x is 0, we get -1 here, and another -1, which is +1, which is positive, and therefore the shape at this point on my diagram will be up and down, because that's what happens when it's positive. And because that's telling you that as x moves past this point, the value of dx on dt goes upwards, and so it goes from being negative here to being positive here. So just as a so dx on dt is positive here, and dx on dt is negative here. Okay. Sweet. And so I'm going to make a connection in my brain that will help me remember this without having to do all of that, remember all of this, and is that, well, positive means the arrows point outwards, and negative means them point inwards. Because that positive should be away, right? And that positive should be out and negative should be in. So that's great, that makes sense to me. Okay, so this is called an unstable critical point, because if you're even very close to this, you'll move away from it. Whereas one where they're both pointing inwards is called stable, because if you're very close to it, you'll just keep, no matter which side you're on, you'll just move inwards again. And I believe your lecturer calls this semi-stable. So what we have now is that if you have dx on dt is f of x, even if there's another variable involved with the beta, which counts as a parameter, then critical points happen when f of x is 0, and then each beta would have a different collection of critical points. But you could draw a graph of x and beta together of what this formula tells you, and that would be where all the critical points are for every possible beta and every possible x. And then it will be, if the derivative of that is negative, then it will produce this thing, which will be stable. And if the derivative of that is positive, it'll produce this thing, which is unstable. And that goes for a specific beta. And if the derivative of that is 0, that's the only way you can possibly get semi-stable points. Okay, and this is where bifurcation comes in. Bifurcation point is one of these points. They are called bifurcation points. But important to note that to be a bifurcation point, you have to both have this being 0 and this being 0 at the same time. So I remember an assignment where they just straight up said, what are those two equations, and you solve them simultaneously. And that gave you a collection of x's and betas which draw on a diagram. So here's the thing. For different betas, I will have to draw a different one of these diagrams. And every beta will have one of its own. And so what I can do is I can say these are all the values of beta, and there will be all these, in my head, this is what I'm imagining, there's all these different phase lines that go with each of those betas. And that's what's in my head when I imagine this. And so at any moment, no, just wait. What we normally do is we just draw this, that's beta and that's x. And we draw a diagram that collects all these critical points together. And you follow where it goes and you get lines like that. And what happens if you draw the curve that's got variables x and beta equals 0, and you draw that curve on this diagram, it will follow where all the critical points are in all of those phase diagrams. Yeah. So when, I didn't have a beta in my other one, but just pointing that out, that's what happens. I know, probably can't look like that, but it's okay. And so these are, the idea is that if you happen to draw a phase diagram there, these would be the critical points that go with that value of beta. And the phase diagram here, there's only one critical point for that value of beta. And bifurcation points are points usually on the diagram where the number of critical points changes as you move this line along the graph. That's my understanding of what they are. And they all have different names based on the shape of the graph at the point nearby to that point. So, yep. Yep, so the number might not change, but whether they're stable or unstable will change. So if you kept following that line in the direction where you thought it was going, it switches over from stable to unstable. Okay, cool. All right, so there's one final thing. Each one of these phase lines has a spot where it's stable or like the critical points on it are stable or unstable, and you need to somehow draw that in your diagram. And so what you would do is that maybe if they're stable, you'll draw them as solid lines, and if they're unstable, you'll do them as dotted lines. Is that right? Okay. But you can tell they're stable or unstable by the value of this on either side of the line. So this is what happened in the other one, and I really need an example now. I think that's what I should do right now. So how are we all feeling about that vibe? Yeah. Because now we would like to know how to actually get this picture, is what you're wondering? Yeah. Because I have a feeling that finding the bifurcation point is great, but you really need to know what the value of... So the thing is, we know that along these lines here, the value of f of x and beta is 0 definitely on all of those lines, because they are the critical points. And I also know that since it's like a two-variable function, its value, and it's probably continuous because you wouldn't be able to differentiate it otherwise, its value will cleanly move from negative to positive as it crosses this line. So I reckon this entire region here will be either positive or negative, and this entire region will be positive or negative, and this entire region will be positive or negative. So I don't think this diagram is possible, but just disclaimer. Diagram like this might never happen. Just in case in the future I'm looking at the notes without watching the video and I don't remember that. Okay. Actually, I can tell on this side at least what's going to happen. If I'm going to cross, if this is going to be stable, then it's pointing inwards at this point, which means that the value of fx beta is positive in this zone here, and it's negative in this zone here, and it's negative in this zone here. Yeah. So negative here, positive there. Oh, this is unstable along here then. No, semi. Oh, crap ass. Okay. There's not a symbol for that. Okay. Anyway, so I reckon that's what we need to do. Can someone give me one? Do I just try and see these? Okay, well, sure. Fine. Cool. But the new phase get easy off the equals and so I feel way more. Trying to wrap what's in each set, we get a bit of a ones. The problem with some of these is that we have to be building. I have to read this, must be open, common point of this market. How then you do it? The question of is really like that. Is it especially with this, and so this is like what we need. Obviously, this is like then you get all this example of the whole process. That's what I'm saying. I know. That's like okay. There are pieces. Let's see what the partial differential equation. But you have to read it. But you have to read it. And the board you have to read it. So the video particularly often there's an analysis of two things and it's not and it's actually we example so there's a the thing that in this one to yeah so I couldn't keep that like or the comments on the show okay the question for always the next always the next factor like the next but sometimes you don't have to so that's more in say that wasn't there something but that's for the solve could be that could be things right so that's why it's such this so that's the idea it's not something you can get two things and that really different like as I and they have things to do things like you know maybe so it's also get